Hi, and welcome back to London Matt's Outreach. This week we'll be talking about sequential logic, which is the third part in the series, Mathematical Aspects of Computer Science. Up until now we've seen certain logic gates and we've seen how to combine them to make circuits that can compute outputs given inputs. But this week we'll see a version of this that is much more intricate and allows you to do much more powerful things with a computer, and this goes by the name sequential logic. So without defining this term now, I'll begin and try to motivate what sequential logic is. So the first thing we're going to be talking about are things called latches. So let me first give you some background and some context before introducing the definition of a latch. Up until now, in the previous 2 weeks, we've been talking about combination logic. But since I haven't defined this term, and I don't think it's useful to give you a full definition of what combination logic is, let me give you an example to illustrate what it means. So here's an example. This is a 1-bit adder, as we saw last week, and in particular this adder has a carry bit. So this is a full adder as opposed to a half adder which would omit this carry bit. Conceptually, think about how this works. You put in inputs, which in this schematic diagram are given by these switches which can be turned on and off. The inputs flow along the circuit and then they result in outputs. So conceptually what's going on is you give it some information, it does something with the information, and then it tells you the result. But the important thing is that for our purposes, this is a time-insensitive process. What does this mean? If I give you some inputs A, B, and carry in, they go through the circuit, and then they give us some outputs. But it takes some time for all of these signals to actually go through each of these logic gates. For instance, if you made this circuit in real life, it would take some amount of nanoseconds to get to this gate, and then it would take some more amount of nanoseconds to get to here, etc., etc., etc. So although we like to think of this as an instantaneous process, because it takes so little time that it doesn't really matter for our purposes, it actually takes a bit of time. But when we're thinking about combination logic, meaning a straightforward linear process that starts here and finishes here and doesn't go back on itself, it doesn't really matter how long this takes, because for all practical purposes we can ignore all this time, because we don't actually care about what's happening during the computation, we only care about the result. Another feature of a circuit like this is that the current state of the inputs entirely determines the outputs. So if you look at the current state of the inputs, that tells you, that's all the information you need to know to see what outputs you're going to get. For instance, the order in which I press these switches has no bearing on which outputs I get from the circuit, because the circuit inside has absolutely no way of remembering the order in which I press these buttons. So this is the kind of thing that characterizes combination logic. In combination logic, you have inputs, they entirely determine the outputs, and there's no memory involved, and there's no time involved, at least on a conceptual level. So one question you can ask is whether the order of switches being activated matter. And as I said, the answer is no for combination logic. Why not? Well, the circuit has no memory, as I just said. However, this leads us to a problem, right? Computers remember things. When you use a computer, your computer uses memory, it uses disk storage space, and it even remembers things temporarily in the processor. So in order to do this, it has to have some kind of way of implementing memory using logic gates, because as we saw in the previous 2 lectures, logic gates are the building blocks for computers. So one thing you may have noticed when we talk about combination logic in the last 2 slides is that these logic gates never feed back on themselves. And this is precisely why we live in the world of combination logic in that context. So instead, let's try to look at what happens when you actually insert a feedback loop into a digital circuit. So here's an example that I made. There's a switch, which we can toggle on and off. Right now it's off. It goes into a NOR gate. So right now it's passing a 0 into a NOR gate. This NOR gate's output goes to a light bulb, but the output also goes back into the NOR gate in the other terminal. Now, this wire is off, and you may wonder why I put question marks here. Well, this has to do with the behavior of a NOR gate. If a NOR gate receives two zeros, then it outputs a 1. But if it receives a 0 and a 1, then it outputs a 0. So right now, the NOR gate has no idea what it's supposed to output, because it has a 0 coming in. So what it outputs depends entirely on what it inputs. So there's this feedback loop, and you get this kind of paradox. So what's one way to resolve this paradox? Well, we can turn the switch on. If we turn the switch on, now we have a 1 going into a NOR gate. But if a 1 goes into a NOR gate, then no matter what, the NOR gate will always spit out a 0. So suddenly this wire is on, which forces this wire to be off, so the light bulb turns off. In addition, the wire coming out of the NOR gate feeding back into itself is also off, and therefore we get a 1 and a 0 feeding into the NOR gate. But this is fine, because a 1 and a 0 in a NOR gate gives you a 0. So the circuit is now stable. It won't change, because this is a stable configuration. Now let's see what happens if we turn this switch off. Now we have a 0 and a 0 going into a NOR gate. But if a 0 and a 0 go into a NOR gate, then the output should be a 1. So this wire turns on. So the light bulb turns on. And this wire feeds back into itself, into the NOR gate. But now we have a 0 and 1 going into a NOR gate. And the output should be a 0. So after this signal has gone through this wire and comes back into the NOR gate, the output is again 0. Okay, but now we have 0, 0 going back in. So the output's 1, and then 0, and then 1, 0. And so this starts happening. So as soon as I turn the switch off, this light starts flickering because the state is constantly changing itself. Of course, this will be happening much faster than I can do on this computer because this will be happening on the level of nanoseconds, and I'm just switching back and forth on these slides relatively slowly. But this keeps happening until you turn the switch back on. As soon as you turn the switch back on, there's a 1 going into the NOR gate, which forces the output to always be 0. And so it goes back into this stable state. So this is a bit strange, and it's different because this is time sensitive. It takes time for information to flow through this wire. And the amount of time that it takes for the information to flow through this wire entirely determines how fast this light bulb is going to flicker if I turn the switch off. I encourage you to try this out for yourself. So last week we saw that there's a website called Logically, which is a full circuit simulator. And I gave some instructions on how to use it in the exercises. So I would encourage you to go on Logically. If you want, you can do it now, or you can pause the video. Or you can do it after the video. But I would encourage you to go on the website, plug this circuit in for yourself, turn it on, turn it off, and see if you can reproduce this flickering behavior. So clearly the thing that we had in the previous slide is not something we actually want to use because the output is unstable whenever the switch is off. And that's not useful for a computer that wants to store information consistently. So we'll make a version of this that does this slightly better, which is called an and/or latch. And this is a controlled feedback loop rather than an unstable feedback loop. So let's look at this circuit. We have two switches, one called on and one called off, and I'll explain what these mean in a bit. Then we have wires going into an OR gate, a NOT gate, and an AND gate. So right now, if you take a look at the circuit, there are a bunch of question marks, as before. Let's see why. This ON gate is feeding a 0 into this OR gate. The OR gate looks at the other input, and if the other input is 0, then it should output a 0. But if the other input is 1, then it should output a 1. But this OR gate is coming from this AND gate, which depends, in turn, on the output of the OR gate itself. Now this AND gate also has no idea what to do because there's a 1 coming into the AND gate, and the behavior of this AND gate is determined by this other switch. So here is a loop, and neither the OR gate or the AND gate can figure out what to do because it's contingent on this unknown input. So you get a paradox. Now, let's see what happens when you turn the off switch on. And I apologize for the clash in terminology, but you'll see why on and off makes sense for these switches in a minute. If I turn this on, then there's a 1 going through this NOT gate, which turns into a 0 going into the AND gate. Now, if an AND gate receives a 0, then the AND gate should output a 0, because it doesn't matter what this other terminal will give. This will always output a 0. This 0 then feeds into the OR gate. And the OR gate now has 2 zeros and knows that it should output a 0. So a 0 goes through here. And now this is stable and consistent because 2 zeros going into an AND gate outputs a 0, and 2 zeros going into an OR outputs a 0. And the light bulb is off. Now look what happens if we turn this off switch back off. This is a 0, which feeds through this NOT gate into a 1, which goes into the AND gate. But this is not enough to change the output of the AND gate. It stays a 0. And that 0 goes into the OR gate, and since there's another 0, this stays a 0 as well, and so you get another consistent loop, and the system is stable. You may be able to see where this is going. If I turn the off switch on, then that turns the light bulb off. So you can kind of guess what would happen if I turn the on switch on. So let's do that. Here goes the on switch. A 1 comes into this OR gate, which now changes the behavior of this OR gate, and it outputs a 1. And now we have 2 1s going into an AND gate. So the behavior of this AND gate now changes as well. And this turns into a 1, which feeds back into the OR gate, but then the output of the OR gate is stable, and the output of the AND gate is stable. So now we're in a stable state again, and the light bulb is on. Pressing the on switch turns the bulb on, just like pressing the off switch turns the bulb off. So let's see what happens when you turn the on switch back off. If I turn this off, the OR gate is still going to output a 1 because there's a 1 coming in from this AND gate. And there's still 2 1s going into the AND gate, and so this output is stable. So the circuit is stable again. So if you press the on switch, the light bulb turns on until you press the off switch. In other words, I could flicker this on switch on and off as many times as I want, but the system will remain stable and the light bulb will stay on. Conversely, if you press the off switch, then the light bulb turns off until you press the on switch. Pressing both of these is not allowed, because it does something meaningless. Conceptually, you can think of this as turning the switch both on and off at the same time. If you actually did turn these on and off, then something would happen to this light bulb, and I can't remember exactly which output you get, but whatever it is, it doesn't actually matter, because it's a meaningless operation, and in practice, if you wanted to create a circuit like this, you would never turn both of these switches on at the same time. This is great, though, because now we have a way of storing data. In particular, I build a circuit like this, then whenever I turn this switch on, I'm storing a 1, and whenever I turn this switch on, I'm storing a 0. And this isn't too far off, really, from how an actual computer works. There are different models for this kind of thing, which exist on the level of transistors in modern microprocessors. And while we won't talk about every possible implementation of this and all the optimizations you can do, we'll explore a bit more about how you use this kind of latch to store data. And by the way, these types of circuits which store information are called latches. So, now it's your turn. Take a look at the exercises below and get some more familiarity with these latches. And again, I encourage you to go onto the website Logically and try these circuits out yourself. I think it's good to get some practice actually playing with them and not just writing them down on pen and paper, because it becomes a bit more interactive and a bit more easy to see what's going on. So, I'll see you in the next video.